Hello friends, this video is dedicated to understand the very root cause of magnetism, that too without mathematics. Which introduction can be started with the moving charge and the magnetism. Now we know already that any mass in space creates gravitational field and hence exerts gravitational force on another mass. Also we know that stationary charge and any stationary charge creates electric field and hence exerts electric force on another charge. Now similarly any moving charge creates a magnetic field and hence exerts magnetic force on another moving charge. From ancient time the lodestone was already discovered, okay, from the earth's crust some material Fe3O4 magnetite. This was found and it was discovered in those ancient days only. It was discovered that it is showing two characteristic properties. One thing is, if this stone, it was called a lodestone because when it is tied to certain, always it remained in a particular direction. It showed some direction. Later on we marked it as a north-south, in north-south direction. In that particular direction only it was remaining. If you disturb it also, it was showing that particular direction only. So it was called a leading stone or a lodestone, okay, or its name was a magnetite. From that the word magnetism is very old, but only around 1820 a scientist named Oersted accidentally understood that electricity and magnetism are not only intimately related, but they are the same force, the two aspects of the one and the same entity. Later it was called electromagnetic force, and that's why electromagnetism was developed. So basically very accidentally this was understood by Oersted. What was that experiment? He saw that there was one current was flowing in a conductor and a compass was lying nearby, and accidentally he found that whenever current is flowing, the compass needle is getting oriented in a particular direction. So from that discovery he did a lot of experimentation, and the conclusion was derived that any moving charge creates a magnetic field and hence exerts magnetic force on another moving charge. Now if a charge is moving, current is nothing but a charge in motion, right? If a charge is moving, that is exerting some force here. And how we can say that it's a magnetic force? Because a magnet is getting impacted by that. What's a compass needle? Isn't it a magnetic needle only? Now since a magnet is being affected, this current must be creating a magnetic field, and that magnetic field created by this current is coming into contact with the magnetic field of this needle, and that's why the force is being exerted. That's why we can say that any moving charge creates a magnetic field and hence that exerts magnetic force on another moving charge or another magnet or another piece of a magnet. Clear? Next concept we are going to understand is what is the force experienced by a moving charge in a magnetic field. Let us say the magnetic field is along y, this as it is in x, y, z, 3 axis we have shown. Now along this y direction, then let us say the magnetic field is there. That means the magnetic field lines are aligned in that direction. Now imagine that a positive charge is thrown at a particular speed v. Now your question may be why it is positive charge. The thing is, as well as a negative charge also we can take, but with the positive charge we will derive the concept, and a negative charge only will be in opposite direction. The force experienced by a negative charge. In force, what is the force experienced by a moving positive charge, that we are going to find out. And once we find out the direction of a force, if it is the charge is a negative, it will be minus, so it will be the opposite direction, as simple as that. Okay, now let us imagine that a positive charge is moving in a particular direction and the angle between v and b is theta. Okay, then it was seen that the force experienced by the charge is directly proportional to the charge That means if more charge is taken, more force is experienced. F is directly proportional to V sine theta. See the sine theta component. Now see this V can be resolved into two components. You are aware of resolving vectors, right? So this vector can be resolved into two components. This component is V sine theta, and in this direction V cos theta, also one component will be there. So let me write it, V sine theta. Now the component of the velocity which is along the magnetic field doesn't matter, doesn't create any difference, but that velocity which is perpendicular, though in a 2D it's not looking, but this is perpendicular, right? This is 90 degree. That component which is perpendicular to the magnetic field vector is playing a role, and with that component the force, how much force is experienced by the moving charge, is directly proportional. And also seen that the force is directly proportional to the strength of the magnetic field. So if the applied magnetic field is more strong, it will experience more force. Writing all this together, F is equal to QVB sine theta. Now F is directly proportional to QVB sine theta, but F is equal to some constant into QVB sine theta, and B is defined in such a way that that constant becomes 1. So QVB sine theta, and A cross B, if two vectors, see here B is a vector, velocity also is a vector. So if we take a cross product of two vectors, VB sine theta will come. So vectorially we can write F is equal to Q V cross V. Now here if the charge was negative, here minus Q will come, that's the difference. But this we have understood. And the force can be calculated from here if we know V and B, strength of a magnetic field and with what velocity it is moving at what angle. That is fine. But what is the direction? See, V cross B. What is the direction of a cross product? If we curl the fingers from V to B, the direction will give the force. Now see, V is in this plane and B, from V to B, it's perpendicular to both, so force will be in this direction, right? Perpendicular. Clear? Now to determine the direction of a force, so we used the right hand thumb rule, right? From V to B, if we curl a finger, the thumb shows the direction of a force, which is the right hand thumb rule we used. But however, when the distance, the theta between V and B, if the angle between the velocity of the charge and the magnetic field is 90 degree, then left hand Fleming rule also is used. Left hand Fleming's rule is used to find the direction of a force. How? See, you stretch your middle finger, index finger and thumb in such a way that they are mutually perpendicular to each other. If the index shows the magnetic field direction and this shows the current direction, see, this is another reason why we assumed the plus Q charge, because the direction of a plus Q charge, in which direction the plus Q charge is moving, that is the direction of electric current. You know, right? So if plus Q charge we assume, we are simultaneously saying that this is the current direction. So this is the direction of a current, or alternatively we can say that this is the direction of a positive charge. So if middle finger shows the direction of a current and index finger shows the direction of a magnetic field, then thumb shows the direction of a force experienced. Fine. So this can be utilized only when magnetic field is perpendicular to the electric current. That means in which direction the positive charge is moving, that is at 90 degree with the magnetic field. In that case, left hand Fleming rule can be also applied to get the direction of a force. See here, let us say this magnetic field is the velocity of the positive charge with the magnetic field is 90 degree. So applying this, if V is the charge is moving perpendicular to B, then also the force, same force direction we can get using the left hand Fleming rule also. And also from V to B, if you curl your right hand curl fingers, the thumb is showing the same direction only. So you apply right hand thumb rule or left hand Fleming rule, you can get the direction of a force. But left hand Fleming rule is preferable. Right, left hand Fleming rule is used only when the magnetic field and the current directions are perpendicular to each other. Here, next concept we are going to learn is magnetic field due to a straight conductor carrying current. Now suppose there is a conductor which carries some current, let us say I. Because of this, so what is the magnetic field at any point? Generally, let us say this conductor is very long and this is somewhere near the midpoint of the conductor. Okay. Now, what is the magnetic field here? Let us say that any point is P. The exact magnitude of the magnetic field strength at point P can be calculated. What is the direction of the magnetic field at point P due to current carrying, due to current I? How to find that? Simply using the right hand thumb rule, you keep the thumb along the current, then the direction shown by your curling fingers is the direction of a magnetic field. Okay, so around this conductor, around the current carrying conductor, there will be a magnetic field. So you imagine taking that point P, one circular loop like this. So this will be the direction of a magnetic field. Now this is in total, but at P, what will be the direction of a magnetic field at P? See, it is going like this and coming like this. This means at P it is going into the board, right? So due to the same current, what is the magnetic field strength? What is the direction of the magnetic field strength at a point Q? See, keep your thumb like this, coming like this. So it is coming out of the board, right? So it is out of the board and we can show it like this. This is into the board, into the board. That means it's going in. So you are seeing the back portion that I am showing by a cross symbol. Here it is coming out. It's coming out. So you are seeing the tip. That's why I showed one dot. Here. Now, magnetic field due to a straight conductor carrying current and vice versa means if the current carrying, there is a coil carrying current. If the current is in a coil, what will be the direction of the magnetic field? See, use the same finger, it's the vice versa. If a thumb is the electric current, the curling of a finger shows the magnetic field. If the current is in form of a coil, then curling finger if shows current, thumb shows the direction of the magnetic field. This is the direction of the magnetic field. Fine. Now see, this is only one line I am showing, but it is diverging in nature in fact. So how it is like? The magnetic field is like this, and if we will go like this towards the end, it will be circular. So it is B. B is going like this. Now, if a current is carried in a circular coil that lies as a small bar magnet. From your earlier classes, you have done this kind of experiment already. You are taking a magnet. Is red visible? You took one magnet and you kept one glass plate on that, and there were some iron fillings you kept here, and you tapped the surface, and the iron fillings were arranged in a particular fashion along some certain lines, right? Along certain lines they got aligned, and again you disturb this, again you tap this, and they got aligned. if this side was north, this side was south, it was coming out of north, going into south, all those things we assumed. But what we saw in eyes are they got arranged along some pattern like this. Okay, now see here also, if you are seeing, this is the current flowing, right? Now these lines, field lines, if you will see, these are this kind of things. So going out, and these are coming in, coming in. So these kind of patterns are coming. So we can see that a current carrying loop is similar to a bar magnet. So the point where students generally get confused is if the current and a magnetic, the directions of a current and a magnetic field induction are vice versa. In both the ways, the right hand thumb rule can be used. If current is along a straight line, around it the magnetic field will be generated. If magnetic field is along a straight line, around that current will be there. But magnetic field will not be there. If a current is there, if current is in a circular loop, your curling of a finger shows the direction of current, then thumb will show the direction of the magnetic field induction. And if the current is flowing in a straight line, keep your thumb in that direction, the curling of a fingers will give you the direction of the magnetic field. Now please try to understand that it is not something like this. This is not, it is not physically existent. I mean, you may not able to touch it. Okay, only this is one explanation, seeing this pattern, etc., and from other implications. So we explain it this way. What is concrete? What we are seeing, that this is the conductor. It is a copper wire or something like that. In that current is flowing. We can see this. And here also the current carrying coil only is the real thing. The other portions are our interpretations. Clear? Next concept we are going to learn is force between two parallel conductors carrying current. Imagine that there are two long straight conductors parallel. They are carrying current in the same direction. Now, what is the force between these conductors we are going to learn? Let us name this conductor as let us say C1 D1. I current is flowing in this. I1 current is flowing in this. I2 current is flowing in the same direction along this conductor. Let us say this is C2 D2. Okay. From C1 to D1, I1 current is flowing. From C2 to D2, I2 current is flowing. What is the force of attraction or repulsion? What is the force between these two conductors? So we are going to learn. Let us find out what is the force due to I1 at a point P along C2 D2. Now, you imagine only the point. For the time being, you forget about C2 D2. Now, the point is there because of C1 D1 or because of I1. What is the magnetic field created at a point P? That we can imagine a circle containing P on its periphery and applying that. See, this is your current direction and you curl your finger. So at P, the magnetic field induction at P due to I1 will be into the board, right? So into the board like this, that I am showing like this. Let us say this is because of I1, this magnetic field is, so B1 I am writing, and this is actually not in this direction but it is into the board. In 2D I am showing like this, that's why I am writing it as into. That means into the board B1 is there. This is I1 direction, you are turning it, so into the board it is going, right? Now at P we have got the direction of the magnetic field. We got the direction of I. Now we are going to calculate, we are going to see what is the direction of the force experienced by P. Now see, we can here use the left hand framing rule because since this is into the board and I2 is moving this way, these are perpendicular to each other, right? So if B and I are perpendicular to each other, we can apply left hand framing rule as we have discussed already. Now apply the left hand framing rule. Stretch your index finger, middle finger and thumb in such a way that they are mutually perpendicular to each other. The index finger should show the B. So this is into the board and current direction is shown by the middle finger. So B is into the board and it is outside. So thumb will show the direction of a force. Yes or no? So force is inside, right? So from P, the force direction will be this force, right? So P will be pulled towards I1, right? Now, similarly, now you forget about the C1 D1, this I1, because of a C2 D2, that is the current I2 along C2 D2. Because of that, what is the force along Q you find out? Let us say there is a point on C2 D2 and the distance between the wires are A, let us say. Some distance is there, right? So at Q, what is the distance? Let us say Q is a point which is on C2 D2, okay? It is at a certain distance. Now, similarly, what is the force experienced by Q due to I2? We are going to find out. Now, from I2, for the timing, as I said, you forget about the C1 D1 and just think of a Q. Q is a point, and because of I2, we are going to find out the force experienced by Q. Now, I2 is this direction, and if we keep the thumb of a right hand thumb rule, keep the thumb this direction, in which direction the fingers are getting curled, that will show the magnetic field experienced on Q. If I will show that in so from Q, magnetic field will come out of the board, right? So again, out of the board, it should be like this only, but I am showing in 2D just like this. This will be B2 because it is the magnetic field due to I2. That's why B2 I am saying. This is out of the board. Now again, at Q, we know the direction of a magnetic field, we know the direction of a current, and we can find out the direction of a force using left hand Fleming rule. So this is out of the board, and this index finger is showing the magnetic field, right? So out of the board. Let me keep it this way. Then current direction is upwards, right? I1. Current direction is shown by the middle finger. So current direction is shown by the middle finger, and the B2 is outside. Then force must be shown by the thumb direction. So this is again inside, right? In this direction, a force will be experienced. Now let us call this F1, F2, and if we do the calculations, we can come to the conclusion that F1 is equal to F2. Regarding that calculations, you can refer your NCERT book, the derivation is available, okay? I'm just explaining you the concept here without doing those mathematical derivations. So when two currents are flowing in the same direction, the conductors are attracted towards each other. The force between them is attractive in nature. Now we will see if the currents are passing in opposite directions, and here you will participate more. Along with me, you will do this thing so that you will be well versed with the application of the right hand thumb rule and the left hand Fleming rule at the same time. Let us say I1 is flowing in this direction and I2 is passing in opposite direction, okay? And what is the force between these parallel conductors? Force between two parallel conductors carrying current was the topic, right? So here also force between two parallel conductors only we are carrying, but the currents are flowing in opposite directions. Now again you follow the same thing. Let us say this is C1 D1 and this conductor is a C2 D2, let us say. And first consider a point Q here, P we took, right? Consider a point P here, and due to I1, what is the magnetic field at P? You keep your thumb in this direction, right hand thumb rule, you turn it. So this is into the board, right? Into the board I am showing. Okay, here into I had written, so this is out of the board I am writing. Here it is into. What is that? Magnetic field. B1, because it is due to I1. So into the board. At P, what is the direction of a force? Now see, at P we know the direction of a B, we know the direction of a current, we have to find out the force direction. So apply the left hand Fleming rule. B is into the board. So this is the index finger is into. But current is down. This is into and current is down, I2 direction. So this is the force direction, right? So force will be outside. This is some force. Let us say F on C2D2 or F1P. This point is P, so F1P. Okay. Now, similarly, what is the force experienced by C1D1 due to I2 current? So, for that we imagined a point Q here. Okay. And due to I2, what is the magnetic field at Q2? Now see, I2, right hand thumb, keep the thumb along the direction of I2. Is it visible? Keep the thumb in the direction of I2 and curl your fingers. Whatever is the direction of your fingers, it is into the board, right? That means the magnetic field induction at Q due to I2. The magnetic field induction at Q due to I2 is into. So this also is into. So it is B2 because it is due to I2, right? So B2, and this also is into now. Okay. Now at Q, we know the direction of the magnetic field. We know the direction of a current. We have to find out the force direction. Now take your Latent-Fleming rule. If B is into, that means into the board I have kept my index finger, and I1 is towards up, it is going. I1 is this. Then thumb is outside, right? So Q will experience a force outside, right? Let us say this point is Q. So this force is experienced outside. Let us say this FQ. Okay. So here you can clearly see that FP, FQ are pushed away from each other. That means two parallel conductors, if currents are flowing in opposite directions, they are repelled by each other, and if the currents are flowing in the same direction, they attract each other. Okay. So these two you can remember easily in a different way. Now see, if your eyes are from upside, from this side if you are looking, in this case I am saying, let us say this is case 1 and this is case 2. The case 1 means current flowing in the same direction, case 2 means current flowing in opposite directions. Now in case 1, if you are seeing from the top, these conductors will look like two dots, right? 2 points. So case 1 I am showing, that's the currents are flowing in the same direction. This dot and this dot, 2 dots you are seeing. Now because of this, there is a loop around it. You think of the magnetic field around it. The magnetic field, this green circle I showed like this. In green I had shown. Now also let me show in green only. So let us say this. It is only closed path. I don't think that it was circular. Now sir has made as a square and all those things. It is a closed path. Now about P, this point was Q, right? So about P also there was another closed path like this. About P also. Now what is the direction of a Q? See, direction of a Q. It was I, if we will keep our finger, it is coming like this. So this direction is like this, and keep I1, it is coming like this. It was about Q, what a circle was there, it was anti-clockwise direction. This also is anti-clockwise direction, right? So see here, anti-clockwise, you put the direction of arrows like this, it was, and about P also it was anti-clockwise. So put it like this, like this, like this, like this. Now you see at the center, the same effect is they are cancelling each other, right? So you can think that they will cancel each other. There is no role of here. So it will act as if this is one loop only. And when this will be one loop only, when the current is flowing in one direction, about that if we will keep, the current will be one loop only. That means though two conductors are there, they will become one conductor. Then only it will be possible, right? When they will become one conductor, when they attract each other. Fine. So attraction will be there when currents are flowing in the same direction. The case 2, let me show you. Remember that it is not happening this way. I am showing just one trick to remember it. Now I am teaching it, that's why it is fresh in your memory. You remember, but time will come, you may forget again. This way, this is a trick to remember things easily. Now case 2. Again here Q is there, here P is there. But charge 1 current is flowing out of the board. From Q it is out of the board, and from P it is into the board it is going. So out of the board means it is anti-clockwise, right? So if you imagine one loop about this, it's anti-clockwise. But into the board means it is clockwise, right? So if you imagine this, it will be, if let me show in a black color, clockwise, 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 clockwise. Now see, here it is opposite, but in between the magnetic effect is added up. Okay, so you can think this way that two people are there, in between the wall is stronger now, means the separation increases. So in this case P and Q will be repelled by each other. Here if current is flowing in one direction and current is flowing in opposite direction, they will be repelled, whereas if both the currents are flowing in the same direction, they will be attracted. Clear to everybody?